I'm Mose Isley. You've seen me in such fine quality, epic chemistry educational videos as chemical reactions in the cantina and do TIE fighters really shoot ions out of their cannons? Okay, today we're going to be looking at part of chapter 4. Getting into the concepts of basically looking at aqueous solutions, types of reactions that get covered in this chapter. But we're going to be looking specifically at aqueous solutions today. And this is the cute, of course, the opening act, if you will. But when you think about it, the parts of the solutions, there's really few main parts. For one thing, what is exactly a solution? Well, a solution, it's a homogeneous mixture. A mixture where everything is pretty much mixed uniform throughout the whole thing. We could look at something like salt water, for example. We could look at sugar water. We could also look at coffee. Yeah, fresh, poured by some poor barista at Starbucks. Yes, exactly. Now in that, we have to look at the two main parts within the solution. There's the solute and the solvent. Okay, what's the difference between the two? Well, the solvent is what actually does the dissolving. Typical solvents would include things like acetone and, one for a lot of people, water. Water is a fantastic solvent. If you stop and think about it, you had a party at your place, you had nachos and cheese because you the bomb. Yo, party ends, you're too tired, you crash on the couch, you wake up, and you see that hard cheese in the nacho bowl and it's stuck. No problem. Fill the bowl with water, set it off to the side, let the wonders of water work its way through and help break those bonds. Oh yeah. And it cleans. Smarter living through chemistry. But that's what solvent does. It does the dissolving. That's why in fingernail polish remover you have acetone. Acetone is great for removing fingernail polish. Okay? Now we also have a solute, which basically a solute is what gets dissolved. It could be coffee crystals, it could be salt, it could be sugar. Okay? So there's a lot of things that can be dissolved in the process. Now there's a couple of other terms like soluble. If we say that something is soluble, that means it can be dissolved. And then we have something called miscible. We never talked about that in regular chem or H-chem. Miscible is just something that is basically liquids that dissolve in each other, and that's pretty much it. We don't make a big deal about that. Okay, let's take a look. So let's look at aqueous solutions. We have mentioned the word aqueous in the other chem classes. OUS meaning full of, aqua meaning water. Think in Spanish, agua. So they are dissolved in water. Again, here's the question, that's the theory. Why is water such an awesome dissolver? That's because the water molecule is polar, not bipolar, polar. Polar in that the oxygen atoms have a partial negative charge. That's because of the electrons that are there. Then, on the other side of the water molecule, you have the hydrogens. Now the hydrogens have a partial positive charge. So if we look here at this water molecule, here's our oxygen, here's our two hydrogens. We have partial negative charges on the oxygens, okay? And then here we have our partial positive charges on our hydrogens. Now you'd say, but wait a minute, why is it partial and not complete? Well, keep in mind that there is a connection. Part of those charges do get used up because of the attraction that they have for each other. So you're not getting the full thing, but you're getting enough of it to make a difference. Okay?
So this, when we look at something like this, where one side is negative and the other side is positive, we have what's called a dipole moment. Not that it's a moment in time. That's not what they mean, but it's dipole. It's a force, essentially, that's there. So you've got water that is polar because it has areas of partial negative and partial positive charges, and that's what allows water to be able to dissolve things because of that polarity. Okay, now what about hydration?
Some people out there would be thinking, oh, hydration, yeah, I play on the football field. I got my big old jug like JR there, you know, because I got to chug that baby, man. Because Coach says I have to stay hydrated. What does it even mean, for crying out loud?
Well, here's the idea. Hydration is the process of water breaking the ions of salts apart. Woo! Breaking ions apart, the ions of salts. Now, think about this for any sports team that's going out there working out, including your typical cross-country thugs, Odell, okay? And it's not a good thing for salt to build up in the body. It really isn't, okay? And you also lose a lot of water because you sweat. Yeah, okay? But why? Why is it, again, that water is able to go and break up the ions of salt? That's because the salts have charges on them. They have positive and negative charges on them, okay? And they attract the opposite charges on the water molecules. That's why you got this picture right here. That should be a reference for some of you. Now, for those of you who haven't been there before, Paula Abdul sang a song in the 1980s called Opposites Attract. And that's why I have a picture of her there to remind people about opposites attract. Yeah, just like that. Okay, so now, here's the thing. Part of the trick in AP Chemistry, you're going to have to learn how to draw. Yep, you're going to have to learn how to draw. Now, some of you would sit there and say, you know, Canu, frankly, you draw stickman figures better than I can. Probably so. I got a PhD in stickman art, but you are going to have to do some drawing. You cannot avoid that in the chemistry exam, and I'm going to get you ready for that. So here we got the famous artist Bob Ross. He has passed away since then. What they call draw a beaker with water in it. Now we're going to do something fairly simple. We're going to go ahead, draw a beaker with water in it, and we're going to use a symbol to represent the water molecule. In this case, we're going to use a triangle. So very quickly, I'm going to go ahead and I draw a beaker. Woo! Very complicated, isn't it? You notice how difficult that was for me to draw a beaker. Oh man, I'm already tired. Whew. Okay. All right, let's get back to work, boys. Break time over. We have a water molecule, okay? So we have a draw beaker with water in it. So the idea, guys, is that we would be able literally to do that. That's what a beaker with a bunch of water in it, that's what it's going to look like. Okay. Hey, speaking of beakers of water, I need a drink break. I have to stay hydrated to do this. Okay. Hopefully there are no questions, but remember, you can pause, you can reflect on this video, you can reflect on some other things I don't want to know, okay? But at this point, guys, I'm going to go ahead and I'm going to erase this. So you can see, remember, you can pause this, you can rewind it if you want to hear me all over again. Okay, let's keep moving. So here's another one. We're going to do something a little bit different. Now we're going to be adding salt to our beaker of water. How in the world is that? What is that going to actually look like? Well, here's a great opportunity here for us to do some drawing. So I'll get a little fancier with the beaker. Okay, calm down, DJ, it's not that bad. Okay, you have got this beaker here. We have some water. Now, for the sake of argument, we're going to assume there's more water than salt in there. Okay, so we'll just throw some triangles in there. That's our water molecules. Okay, then we're going to go and draw a salt molecule. Now in this case, notice how I specified what was what. You will need to do that. You'll need to do that anytime on the exam. As long as you indicate what you're doing, they should be able to follow it. It's pretty easy. Now, is there some magic number for how many you're supposed to draw? Not really. Remember, the general idea is that you're showing salt that's in the water. Now, here's the thing though. You put salt in there and you kind of notice, wait a minute, salt does not do that. Salt doesn't do this in the beaker of water. You're right, it doesn't. Well, what happens? Remember, salt has a positive ion, the cation, the positive ion, and the chlorine would be an anion, a negative ion. Well, what happens to the salt when you put it in the water? And it's not too much salt, because if you put too much salt in there, it's not going to dissolve very well, right? Because you're going to have a bunch of salt that's going to settle to the bottom. Ugh. And that would be a pain. No. So really, this is not an accurate drawing. It's not. And some of you are saying, Canu, why did you have us draw this? I'm taking you down the path. And besides, hopefully you didn't draw it in pen. Okay? So what's happening? What happens with the salt in the water? Well, what happens is the salt gets broken up. It gets broken up because the water does the job. The water does the job breaking it up. And if you notice, are you noticing something about the water? Notice how the water is surrounding the salt, the sodium, the chlorine. Notice how it is surrounding this. No, I'm not making some German cross. That's not it. The idea, though, is that the water molecules, remember, they are tearing apart the salt. They are surrounding the individual ions of the salt and yank, pull it away. And that's where that hydration comes in. This is what we're talking about when we're talking about hydration. Now, is there a better way to look at this? Yeah, there is actually. Okay, but I'm going to go ahead and erase this. Okay? I'm going to erase this. I'm going to move on. Here's one way to look at the hydration, where here is a salt. You've got a cation and an anion. Remember the positive ion, cation. The anion is negative. So here's your chunk. And what's happening with the H2O? Well, the H2O is surrounding itself around these particular ions. They help break it off, and then they put them together. And here's what you've got here. Here's your oxygens that are now surrounding the positive ion. It doesn't have to be sodium, guys. It doesn't. It could be potassium, for example. Any cation that's going to have a positive charge, it's going to attract the oxygen side of the water molecule in solution. Well, why? Well, remember, water's polar. It's got negative sides and positive sides. And Paula Abdul told us the truth when she said opposites attract. And that's what we're seeing here. We're seeing here, in this case, here's our positive ion. Here are our negative, partial negative charged oxygens on our water molecules. They're surrounding it. You go here, now you're seeing the opposite. You got a negative ion in there. Could it be the chlorine? Yeah, it could, because it could also be bromine, it could be iodine. There's different ways to look at it, okay? But they're ionic compounds. So that's what's happening here. And then surrounded, this negative ion, okay, is now surrounded by the water, the partial positive charge is connected to it because of that opposites attract thing. Okay? All right. We got to switch gears a little bit because now we got to look at solubility. Solubility has to do with, hey, how much can something dissolve in a certain amount of water? Because let's face it, if you try to make coffee, okay, if you put too much coffee in, you'll have a really strong cup of coffee, but a lot of the coffee is just going to drop to the bottom, and that's it. Okay, and you are going to look silly because you just wasted the coffee! Now usually we do this solubility in grams per 100 milliliters. They are not, the AP Chem people are not going to have you read solubility curves, although I think it's a disappointment because that's something that's not particularly difficult. Okay? Excuse me. So, when they do dissolve, okay, the ions are separated and can move around this substance. Now, water can also dissolve non-ionic compounds if they have polar bonds. How come? How come? Pause it and think about it. Why is it water can also dissolve non-ionic compounds? What, you mean they can be covalent? Yes, if they have polar bonds. Remember, it can have polar covalent, right? How come? Pause, think about it, and get back to me. And we're back. How come? Remember, the opposites, the polar. If the bonds are polar and the water is polar, they will naturally attract to each other. Okay? Paula Abdul, opposites attract. Now, of course, here's the question. What dissolves sooner? A giant cube of sugar or powdered sugar? Here's another moment. Take a moment to pause and think on that one. Go ahead. I'm here. I got the time. Pause and think about it. Powdered sugar versus a cube of sugar. And we're back! So the question comes down to is what dissolves sooner? The giant cube of sugar or the powdered sugar? It's going to be the powdered sugar. How come? How come? Two words. Surface area. Surface area. If you have more surface area exposed to a solvent in a solution, then the solute, what gets dissolved, is going to break down even faster because more of it, ladies and gentlemen, more of it is being exposed. More of it's exposed, more chances of hookups being done through the wisdom of Paula Abdul. Opposites attract. Yep, go figure that. All right, let's move on. We got to talk a little bit about electrolytes here. Now, those are substances that dissolve into ions. Now, the thing is, dissolved ions can, in fact, move. They can move. All right? Now, solutions of ionic compounds can conduct electricity. It allows ions to flow through. It allows electricity to flow through. If we were to go and take, what is that? Distilled water. You can't get much more pure than distilled water. And you try to run electricity through it. You're going to be very disappointed because there's not going to be a lot of electricity that's going to go through. Throw in a little bit of salt. Throw in some minerals. Now you're talking. You're going to have more conductivity. Is it the water itself that allows the conducting of electricity? No, it's not. It's the dissolved ions that are mixed with the water that will allow the conduction of the electricity. That's the key, okay? So when we look at electrolytes, there's a couple of ways we can look at them. There's strong, weak, and non-electrolytes, okay? Now, we can look at the main electrolytes in body fluids. For us, yes, body fluids. I said it. Body fluids. Get used to it. I'm running out of time here. Guys, sodium, chlorine, magnesium, calcium, and potassium. Big, big important things, huh? Strong electrolytes completely dissociate, fall apart into ions. They conduct well, like strong acids and strong bases. I will let you pause and write the examples there. All right. Weak electrolytes only partially fall apart.